In most cases, you will not find simple interest very often. You're instead going to discover that most interest is either compounded over a specific period of time, or it can even be compounded continuously. So we're going to need new formulas to work with compound interest. Notice this section of formulas we have here. We've already covered simple interest back in lesson 3-1. But when we are looking at compound interest, that simply means that we're going to earn interest over a certain interval. It doesn't have to be a year. Remember, with simple interest, it's always an annual interest rate. So you only are earning interest one time in a year. With compound interest, you might earn interest monthly or quarterly, even daily. And so because we're going to be getting interest paid on top of the interest that we've already earned, our formula has to adjust a little bit. And you will see this compound interest formula right here. It looks similar until you get inside the parentheses. And what you will have to do is take the interest rate in decimal form, divide it by this M value, and the M stands for the number of times interest is compounded in 1 year. So if our problem said we had 6% interest compounded monthly, the M value would be 12 because there are 12 months in a year. If it were compounded semi-annually, that means 2 times in a year, so our M would be 2. And then you notice this exponent outside the parentheses. We have to take whatever that M value is and multiply it times T, which has to be in years. Notice that all of these are defined down here. If you ever forget what the letters stand for in these equations and these formulas, you can look back at this section and see what it is. So as long as my period of time where interest is being compounded is something that's countable, if it's discrete, in other words, I can tell how many times in a year it happens, this will be the formula that I use, the one for compound interest. But if my interest is being compounded continuously, that means I can't count that up because I'm constantly earning interest on top of interest. And our formula adjusts a little bit. You're going to see that even though if we looked at this in table form, we would see that the more often that we calculate interest, if nothing else is changing, the rate is the same, and all we do is change whether it's going to be compounded annually, or if it's going to be compounded quarterly, or if it's going to be compounded monthly, what we would see is that we would have an increase in the amount of interest the more often this gets compounded. So you might think, well, goodness, if it's compounded continuously, that's got to be a huge number. Actually, what happens is it levels off. There's sort of a limit, a boundary that you will not be able to go past whenever you're calculating interest that's compounded continuously. And it's actually approaching the value E, the natural number. It occurs frequently in formulas in business, in the natural sciences. If you haven't encountered this E before, you need to become familiar with it. It's sort of similar to pi. It is an irrational number. That means it's a decimal number that doesn't end and it doesn't repeat. It cannot be written as a fraction. And we're going to take our principal times this natural number E, which is going to be raised to the r times t power. Now again, think order of operations. The only thing the exponent is attached to is the E. So we would have to take this natural number e, and you will have a key on your calculator that will probably either be e raised to the x power, or if you have a graphing calculator, you would have to find the number e, and then you could put the exponent on it. And on the graphing calculator, if it's a TI, your e is the second button, which is typically the top button on the left column, and then you would have to hit the division sign, and that would get you E on your calculator screen. Now, one other thing to keep in mind is sometimes we need to be able to compare interest rates, and it can be sort of confusing if one is being compounded, say, monthly, and a different interest rate is being compounded quarterly, and it wasn't the same interest rate. So I might need to figure out where am I actually going to earn more money. And to do that, we would need this formula, the annual percentage yield or the effective rate. That will allow us to make an apples to apples comparison. So let's go through our homework, or not our homework, but our notes, so you will be able to do your homework. And notice it says, unless otherwise noted, round monetary answers. Anything that's asking you to find money, round to the nearest dollar. Round your percents to 2 decimal places when you write it as a percentage, and round your time to the nearest year. So we want to take $2,000. It's going to be invested in an account paying 1% annual interest. That's about all you can get at the bank right now. It's very difficult to earn very good interest on your money right now. You want to compare the balance after 20 years using simple interest and compound interest. And if it's compound, we're going to compound it once a year. Okay? So, we know that simple interest uses this formula, A equals P times 1 plus RT. That's simple. So I want to know how much money would be there in 20 years if I have invested $2,000. So I'm looking for the A. My P is 2,000. My R is written as a percent, 1%, so I have to change it to decimal form. And that gives me 0.01 times T. And the question is, what will be the balance after 20 years? So T is 20, time in years. Now, if I put this into my calculator, I multiply it out, I come up with $2,400. I will have earned $400 in interest if this is being calculated with simple interest. Now, if I want it to be compounded, my formula is a little different because remember, it's A equals P times 1 plus, we had R over M raised to the MT power. Now on this problem, I'm still looking for the A. P is still 2,000. But the rest of this is a little different in my formula. My interest rate is still going to be 1%, so that's 0.01, divided by, since it's compounded annually, that's 1 time in a year. But don't forget you have an exponent, and your exponent is M, which is your 1 time in a year, times your T, which is 20 years. Now, putting this in your calculator, you would start with your parentheses, 1 plus 0.01. And I'll write this out so you can see. That's going to be 1.01, and then your exponent was 1 times 20, which is 20. So in your calculator, you want to put 1.01 first, raise it to the 20th power. You either will have a button that is an Y to the X key, or if you're using the graphing calculator, there is a little rooftop. It's actually called a caret symbol that is on the far right column. It's under the button that says clear and above the button that's the division sign. So if you type in 1.01 and then you hit that rooftop or that caret symbol and then you type in 20, that's going to take 1.01, raise it to the 20th power. At that point you could hit enter and then times 2,000, and you're going to come up with, to the nearest penny, $2,440.38. So even though they both had the same percentage rate and we were compounding annually, the difference between simple and compound interest amounted to an extra $40.38. Now, this next question wants us to make some comparisons if what changes is simply the number of times in a year that our interest is going to be compounded. So remember, this is our formula, A equals P times 1 plus R over M raised to the MT power. And on part A, it asks us to calculate semi-annually, which is twice a year. So what we are doing is we're putting an investment of $5,000 into an account. So our P is 5,000. It's going to pay 2% annual compounded interest. So my R is 0.02. When I drop the percent and move the decimal 2 to the left, over how many times in a year will it be compounded? According to A, twice a year, semi-annually, raised to the M times T power. My M is 2. My T is 10 years. I'm comparing the amount in the account after 10 years. Okay, so very similar to what we did on the last problem. And again, be careful with your calculator entry. Start with your parentheses. We talked about this before. Don't forget PEMDAS. If I have something inside of parentheses that I can simplify, I want to do that first. So I can take the 0.02 and divide it by 2 and then add 1 to it. Again, that's using order of operations. I would do my division before I add. And that number will then be raised to the 2 times 10 or 20th power. So 0.02 divided by 2 is 0.01. That's going to give me 1.01 raised to the 20th power. Calculate that out, and you get $6,195. $6,100.95. Okay? Let's see what difference it makes. In fact, let's go to C. We're going to do A and C and D. Let's see what happens if we want to compound it monthly. So the only thing that will change in our problem is instead of M having a value of 2, it's now going to have a value of 12. And that would give me 12 times 10 for that exponent. So I have plugged in 0.02 for my R, my M is 12, and my T is still 10. Now, check with your calculator. I want you to see if you can get all your calculator entry in correctly, because you would need to take your 0.02, divide it by 12, and you're going to get a decimal number that doesn't end. So you want to try to retain as many of those digits as you can, add 1 to it, and then raise that to the 12 times 10 or the 120th power. After you've done all of that, you'll multiply it times 5,000. And if you round this to the nearest penny, an interesting thing happens. You have 6105.997. Now, if I round this to the nearest penny, that means this 7 tells me that this 9 needs to round up. And if I round 99 up, it becomes 100. In other words, this is $6,106 even. That definitely went up a little bit from only compounding semi-annually. Now let's just see how much difference it makes if we compound continuously. And this is where our formula changes. A lot of people refer to this as A equals PERT because we have the P times E raised to the RT power. So our P is still the $5,000 that we're starting with. E is a number, and R is my 0.02, T is my 10. Notice there's no M. It's compounded continuously, so I can't count up how many times in a year that is. Now, if you put this in your calculator, you will need to put in the E value. So if you're on the graphing calculator, that's second and the division sign to get the E. Raise it to the 0.02 times 10 power, and that's going to be a 0.2. Take that answer times 5,000. If you've done your calculator work correctly, you should get $6,107.01. Okay, if you're having any issues with the calculator entry, please let me know and I will try to help you with that. That's one downside with taking this course online. I don't have a good opportunity to show you exactly how to do this on the calculator in terms of this video, this teaching lesson, but I can come up with some other ways to help you if you still need some help. Now, next example, you're saving for a down payment on a house. You want to buy the house in 5 years. How much do you need to invest in an account that's paying 4.5% compounded monthly in order to have $10,000 for your down payment? Now, since this says compounded monthly, we've got to decide which formula we need. And as long as it's a countable amount after the word compounded, monthly means that's 12 times in a year, then this is the formula we need to use. A equals P times 1 plus R over M raised to the MT power. Now I need to decide, do I know the A value or is that what I'm looking for? And in this question, I'm trying to find out how much I need to invest now so that I will end up with $10,000. That means I know the final amount. I want $10,000. But do I know the P? That's what I'm trying to find. How much money should I invest now to turn it into $10,000? So if P is the variable I'm looking for, I should know all the other variables in this formula. My R is my interest rate in decimal form, so that 4.5% becomes 0.045, and it's compounded monthly. That means the M value is 12. Raised to the 12 times, how many years do I have to let this grow? 5. So that's how we're going to plug everything in. Now, to solve this, if I look on the right side, can I do what's inside the parentheses? The answer is yes, I can. So if I think order of operations, I'm going to take 0.045, divide it by 12, and then add 1 to it. And here's what I'm going to have. My 10,000 will equal P times 1.00375 raised to the 12 times 5 is 60 for an exponent. So what I need to do is take $10,000 and divide it by this 1.00375 raised to the 60th power. And that's going to tell me the amount that I would need to invest. Now, you have some options on how to get this into the calculator correctly. One thing that you can do is hit the 10,000 divided by, and then just make sure you open a parentheses before you do the 1.00375 raised to the 60th power. Don't close the parentheses until after you've put the exponent on. Otherwise, your calculator will think you're trying to do something different than what you really want it to do. And if you calculate this out, you get a starting value, an amount that you should invest, of $7,988. And if I round this to the nearest penny, it will be 52 cents. Okay, here's a follow-up question. Before you invest your money in the account in this problem that we just did, it should say problem 3, you find another bank that pays 4.75% compounded quarterly. Will this account allow you to invest more or less money than the account that's in problem 4? So, we're going to have to make a comparison. If we start with our formula, A equals P times 1 plus R over M raised to the MT power, what we want to figure out is if we change this interest rate, will we need more money or less money to go into the bank in order to have the $10,000 for our down payment? So we still want $10,000. We're looking to see what amount we need to invest. If we're now investing at 0.0475, because that's my interest rate in decimal form, divided by the word that follows compounded is quarterly. And that means there are 4 quarters in a year. You can think of it the same way as there are 4 quarters in a dollar. And then my exponent will be 4 times 5. Because we still are trying to end up with $10,000 in 5 years. So if you put all of this in your calculator, and I'll give you a moment to compute that. Remember, start with what's inside the parentheses, get that value, raise it to the 20th power, because 4 times 5 is 20, and then you need to take 10,000 and divide it by that number. Be careful that you don't round too soon. You will get the wrong answer if you round too soon. We're going to come up with $7,897.01. Now, if we compare that to what we found on the other problem, we needed $7,988.52. So this account would allow us to invest less. Our interest rate went up, even though the compounding period went down in number because we went down from monthly to quarterly. The fact that the interest rate was higher meant that we could actually invest less. Now, that's not always a given. You're going to have to calculate and compare because there are other factors that can affect that. All right, Susan is going to invest $2,500 for 3 years in an account that pays 3.5% annual interest compounded monthly. I'm going to underline that because that's a good reminder about what formula I will need. At the end of that time, she moves the money to a different account that pays 4% annual interest compounded quarterly, and it stays there for an additional 2 years. Can we figure out the value of the account at the end of that time? Yes, but we're going to have a 2-part process here. So we're going to have to start with the first part of the problem. Since it's compounded monthly, I know this is the formula that I need. And here's what we know. She's investing $2,500, So I'm going to try to find the amount she has after she invests $2,500, and the account is paying 3.5% annual interest compounded monthly. So my rate is 0.035. Compounded monthly means that's divided by 12, raised to the M is 12 times, I'm going to leave it there for 3 years. So my T is 3. Now make sure you understand where all these values came from. And again, calculator entry means start with the parentheses. So you're going to take the 0.035, divide it by 12, and then add 1 to it. And that gives you kind of a long decimal number. You will then need to raise it to the 12 times 3 or 36th power, and then you're going to multiply that times 2,500. That's the order you go through in putting it in your calculator. So at the end of 3 years, she has $2,776.35 in the account. Now, we're not done, because at the end of this 3 years, it says she moves the money to a different account that's paying 4% annual interest compounded quarterly, and it's going to stay there for 2 more years. Let's see if we can get the final value of the account. So this money is going to transfer into a different account. Same formula, and I know that because it's compounded quarterly, and that's a countable number of times in a year. So I want to find the final amount after this $2,776.35 gets put into this other account, where it's earning 4% interest, so 0.04, compounded quarterly. Quarterly means 4 times in a year, and it's going to stay there for an extra 2 years. So my M is 4 times my T is 2. There we go. Now I think you can see it. Put that in your calculator, and you should come up with $3,006.39. Okay, now we need to learn how to make that comparison with APYs in order to see what would be a better deal. So by comparing their APYs, decide which investment is better. An investment at 4.26% compounded monthly, an investment at 4.3% compounded quarterly, or an investment at 4.38% compounded semi-annually. Now to do that, we need that formula for finding the APY. And all we have to do is take 1 plus R over M, raise it to the M power, and subtract 1 from it. That's how we can come up with the effective rate. So if we take the first option, the 4.26% compounded monthly, okay? So if it's compounded monthly, we're going to have 1 plus 0.0426 divided by, monthly is 12, raised to the 12th power, and then we'll subtract 1 from that. So again, putting this in my calculator, take your fraction, 0.0426 divided by 12, add 1 to it, then raise it to the 12th power. When you subtract 1, you end up with an annual percentage yield. Your effective rate is going to be 4.34% when you put it back into percent form. Okay, 4.34%. Now, we need to calculate the second one, which is if we're investing quarterly. So our interest rate is a little higher. It's 0.043, but quarterly means that's 4 times in a year, so we'll divide that by 4. raise it to the fourth power, and subtract 1. So if you put that in your calculator, you're going to end up with 4.37% when you take it back into percent form. So you should have had 0.0437 when you looked at your answer in the calculator. The final one we'll do is semi-annually, but it has the highest interest rate of all. So let's see what we come up with. That would be 1 plus, and 4.38% becomes 0.0438. Divide that by, if it's compounded semi-annually, that means 2 times in a year. And we're going to raise it to the second power. So the APY for this one, if we take it back to percentage form, is 4.43%. Even though it wasn't compounded the most often, because the interest rate, starting interest rate, was actually higher, it did give us a better yield. Okay? So make sure you do a comparison before you make a decision on which way to go. Sometimes it's not. All right. And our last problem has 2 parts. To accumulate $20,000 on your daughter's 18th birthday, how much must you invest on her second birthday in a CD that pays 4% compounded quarterly? Now again, when I see the word compounded, that tells me I've got to use the formula for compound interest. The word quarterly tells me that it has the M in it, because I can count up the number of times in a year the interest is being compounded. So I want to accumulate $20,000 on her 18th birthday. That's not my starting amount. That would be my final amount, my A. So I want $20,000. I'm trying to find how much I need to invest, so I do not know what P is. That's what I'll solve for. But notice what they haven't told us. I do see my rate, and I see the value for M, but they haven't told me a time. I'm going to have to calculate that, because what I do know is I want this money to be there on her 18th birthday, and I'm going to invest some money on her second birthday. So I've got to figure out how many years that would be. Well, it's not that hard to figure out. It's a subtraction problem. So what that tells me is T is 18 minus 2, which is 16. So when I plug in, I'm going to have 1 plus, my CD is paying 4%, so that's 0.04, compounded quarterly, that's a 4, raised to the 4 times 16 power. Okay, this looks pretty similar to things we've done. Again, start with your parentheses. Your 0.04 divided by 4 will be 0.1. Add 1 to it, and then raise that to the 4 times 16, or the 64 power. That is probably going to give you a very ugly decimal number. You want to keep as many of those digits to the right of the decimal as you can. And our P will equal 20,000 divided by that ugly decimal number, rounded to the nearest penny. That means you should have $10,579.43 invested on her second birthday if you want it to turn into 20,000. So it would take about 16 years for your money to almost double if you're only working with a 4% interest rate. If you have a higher interest rate, it will double more quickly than that. Now, I do want to give you an example of what happens if we're working with the interest that's compounded continuously, and also if maybe instead of solving for the A or the P, we might need to be solving for the R or the T in that equation. So what we are asked to find here is If I only have $10,000, but I have access to invest it in something that will give me interest that's compounded continuously, if I want to grow that to $20,000 in 15 years, what interest rate do I need? Well, the fact that I see the word continuously following compounded is what tells me I need to use A equals PERT. So I will start with that formula. The A is the amount I want to have at the end, 20,000. The P is the amount that I have to invest now, which is 10,000. E is a number, and my R is what I'm trying to find. So that's going to be the variable I will solve for. And T is 15. I want to know in 15 years what would be the interest rate I would need for that money to double. Now, one thing I can do, remember we had said in an earlier lesson, since this 10,000 on the right is being multiplied times e raised to the exponent that has the variable in it, I can make this simpler if I'll go ahead and divide each side by 10,000 first. That is perfectly legal to do that. And that will give me 2 on the left equals e to the r times 15 we would write as 15 times r power. Now, here's where you either need to remember something from college algebra, or if you don't remember this, let me give you a quick tutorial on what happens if you are trying to solve what is called an exponential equation. It's an exponential equation because the variable we're trying to find is in an exponent. So I have to somehow get this variable out of the exponent, and the tool that I use to do that is called a logarithm. Logarithms simply mean we are looking for the exponent that something has to be raised to in order to give us a certain answer. If we were in a classroom, I would go through a much more detailed explanation with you to show you how logarithms are inverses of exponents and how that will actually help you, if you understand that concept, in being able to solve these equations where your variable is an exponent. Let me just remind you that according to algebra, as long as we do the same thing to each side, we are not breaking any rules in algebra. So if I want to multiply both sides of an equation by the same thing, I can. If I want to raise both sides of an equation to some power, I can. In like fashion, when I see that I have a variable in an exponent, I can take the log of each side because logarithms let me solve for exponents. Now, the simple rule of thumb is this. There are 2 kinds of logarithms. There is an log, which is your common log. We use it with base 10, but we can use it with other bases. It's just if I'm using it with a different base, I would need to identify what the base is. We also have an ln, which is the natural log. Now, anytime you see e as the base and you're trying to find the variable when it's an exponent, you're going to want to take the natural log of each side. And when you do that, you need to understand that a natural log means I am looking for the exponent that e has to be raised to in order to give me whatever follows it. So I'm looking for, and we don't typically write the e there because it's understood when I see natural log that the base is e. And that means on the left, I have the natural log of 2, but an interesting thing happens on the right. First of all, anytime I'm taking the log of something that has an exponent, I get to pull the exponent down in front of the logarithm. this becomes 15 times r times the natural log of e. Okay? So if I were taking an log of each side, then I would still pull that exponent down in front, and then I would have had log of whatever followed it. Okay? But there's something interesting about the natural log of e. Think about this for a minute. This is saying I'm looking for the exponent that e has to be raised to in order to give back e as an answer. If I put that e in there, that's what it means. Well, e to what power is e? Anytime I'm taking the natural log of e, if what follows natural log is e, it simplifies to be 1, because the exponent you would put on e in order to get back e is an exponent of 1. And 1 times anything will give you whatever 1 was being multiplied by. So we have the natural log of 2 is equal to 15 times r. We are almost done. You then divide each side by 15, and if I put that into my calculator, I'm going to get 0.046, which is about 4.6% interest is what I'm looking for. Now, I realize this was not a full explanation of logarithms, and for that reason you may feel a little fuzzy. Let me remind you that you have access to the video lessons that I have made for college algebra. And if you will watch the college algebra videos, and in particular, it would be chapter 4, 4.1, 4.2, and possibly 4.3, that would fill in some extra information. You won't probably need everything that's in those videos, but you would find a deeper explanation of logarithms there.